Looking at calculating percent ionization for molar formic acid solution in water. So, the formic acid reaction we went over in this problem with the 8. So we're going to be referring back to it, and we're also referring back to this equation. This is the percent ionization or percent dissociation equation. We're going to need that for this particular problem. And we're using the 8 here, which we calculated already, and got the pH for that and the concentration, this 0.038. We're going to use that and the pH and compare those things later on in the concept check. So I just want you to be aware of where I'm pulling these from. It'll be from exercise 6 and from exercise 7, and we're going to be comparing the values to show the mathematical relationship, you know, because I told you the conceptual, you know, as you become more dilute, your percent ionization increases. We're also going to show you, based off of the numbers, that effect as well. So, starting here, first thing we should do is what? What should we do first? Write out the reaction. Good. And if it has a Ka value, the acid is basically reacting with what? Water. Okay, so we have our formic acid plus the water. Okay, making the hydronium, which is really just the hydrogen ions too, and our conjugate, which is formate. Remember, when you take off the H, it just adds a negative to that particular polyatomic, like so. Okay? So there's our reaction, and what should we do after we have our reaction there? Right, good, as I started it for you right there. Now we're going to do the right. We can put in the initial concentration, which happens to be what? Initial concentration is 4. You don't need to worry about the water, since its concentration is really not changing. Hydronium and the formate would start at what? 0. Good. And since most of these you'll see are always going to, where they're going to be monoprotic or moles of 1-to-1-to-1 kind of relationships, so our change value is going to be what? Minus X from the acid to begin with, and then plus X for the ions that are going to be created over here on the right-hand side of the product. So then this ends up being 4 minus X. This ends up being X. This ends up being X. We know the Ka value. So now what do? We can go ahead and solve for X. So, if you need that step, though, where you need to write out the expression, go right ahead and do so. Writing out the Ka expression, the hydronium times the formate, concentrations over the concentration of the formic acid. Some people need to still do that step. That's fine. And then you substitute in our different values. So Ka was 1.8 times 10 to the minus 4. Substituting in our X values. So on the top, I should just put what? X squared. Okay. On the bottom goes the 4 minus X. And how do I make my calculation quicker? I get to eliminate the X, yes. Remember, really, the 10 to the minus 4 will still check it to make sure that it's less than 5% ionization. It's a good bet that it is anyways, but anything that's 10 to the minus 5 or smaller, you can definitely eliminate the X for the K when you see the Ka is that small. If it's 10 to the minus 3 is really when you need to be concerned about looking at graphing it, because that percent ionization might be greater than 5. So remember that 5% rule that we talked about? You need to make sure that So this actually will speed up your calculation where you do not need to put it into the graph. You can graph it. You're going to get the same answer, though. You're allowed to do that and check yourself by graphing it. But on the AP exam, time is always a concern, so we want to get as quick, get through the problems as quickly as we can. So what is our x value here going to be? Once we multiply the 4 up to the 1.8 times 10 to the minus 4 and then square root it, what are we going to get here for our x value? 0.027, right? Molar. This is going to be for the hydronium. 268, so yeah, we'll go with the Ka has 2 digits, so we'll just go with 2 here. Now you can wait till the N2 and do the rounding at the very end, but yes, at the very end we would go with 266 because the Ka value is considered part of the Sig Fig rounding and consideration. Now that we have that, it wants the percent ionization. So the percent ionization is going to be the percent of the ion over the original concentration times 100, so 0.027 over the 4 times 100. What does that end up being? Point what? 68, okay, yes, 68%. Like that's where I said here we would go with our 2 sig figs. So this is for the 4 molar. 4 molar. That's why I wanted you to look back at exercise 6, because for the 8 molar, this was exercise 6, remember. What was our percent ionization in that problem? It was 0.47% was its ionization. And what was its molarity of the ion, the hydronium? What did we calculate that to be? What was the molarity of the hydronium for that particular exercise? 0.0376, right? Something like that. Well, let's compare and discuss these answers. So we have a molarity of 4, we have the molarity of 8. We diluted it from 8 to 4, right, by adding water. 0.47% ionized compared to 0.68. Did we say that if you dilute it, the percent ionized should increase? Does that numerically agree with that concept? Did it increase as we diluted it down to 4? Yes, it went from 0.47 to 0.68. Now, let's also go over the concentration of the hydronium for the weaker one, the more dilute 4.00 was 0.027. The concentration of the stronger one, the 8.00, or the more concentrated formic acid, this concentration is higher. So the concentration is higher for the one that had the higher original concentration, but the percent ionization is actually lower. So it's kind of like a weird inverse relationship that you see here. Because you would think, hey, well, if it's a stronger, has more concentration, you would think the percent ionization would be higher. Well, that one's inverse. So as you dilute it, the percent ionization actually is increasing. And the basic idea is when you add water, you're adding more into the reactant there, and it's pushing it to the right where you would get more ions out of it. More ions, but less concentration, and that's why it's very confusing. You get more ions, but less concentration, because you have more water in there, and the water's diluting it. So, lots of little nuances with percent ionization, the actual concentration of the ions, and then we're also going to look now at the concept track and look at what happens to the pH. All right, the value of Ka for formic acid solution should be higher than, lower than, the same as the Ka for the 8 molar formic acid solution. This one isn't actually in your notes, but do take a look here and tell me what you think. Why would you say same as? It is the same reaction, yes.
Then it doesn't change, like, because there's no heat.
Good, yes, it is the same as, because the only thing that can change the K value is what? Temperature, and we're not saying we're changing the temperature, so the Ka would have to stay the same. This is kind of that same concept, you know, from the previous unit about equilibrium constants in general. They only change with temperature. Still applies here to the acid-base ones as well. So make sure you mentally remember that the only thing that can change any of the K values is going to be temperature. Okay? So that's a quick little added review. Let's look at our percent ionization. We kind of just talked about this. Percent ionization of the 4 compared to the 8 is going to be higher than. Okay, let's take a look. Why is that? To dilute it, water is being added. Equilibrium will proceed towards the products, really increasing these ionizations as you're adding so much water to it. But do still remember, as we'll see, our concentration actually is lower of our H plus or hydronium. Same thing though, okay? So that idea, when you dilute it, you actually end up with more ions on the product side. But it's relative to how much water has been added to it, so keep that in mind. The pH. What controls the pH? The H plus or the hydronium amount. The H plus or the hydronium amount. And what is that, how does that relate to the pH scale? The more hydronium or hydrogen you have, what's going to happen to your pH? If you have more, it's going to go up or go down. Yes, remember pH scale for the acids neutral is 7. So as you go down the pH scale, you're adding more hydronium or hydrogen. So more concentration, lower pH, less concentration should be a higher pH, right? Does that make sense? That's another inverse one you got to remember about acids because of the way the scale is for pH. So pH of 1 is going to be a lower value, higher concentration, whereas a pH of 2 would have less hydronium or hydrogen in the solution. Okay, and if we compare the one for the 8 molar formic acid, wasn't it like 1.42 was your pH, right? Is that from exercise 6?
Yeah.
So if we were to do the 4 molar one and check it, we would do the negative log of the 0.027. And what would that pH value be? It should be higher than 1.42. So let's check that and see if that actually comes out correctly, and it does. It ends up being like 1.57. That pH value is higher. It's not a lot higher, but it is higher. So do get that idea that if you dilute, comparison of the diluted one to the more concentrated one, the pH value, the more dilute would be higher. So the pH would increase. All right, now on to bases. We're not going to do a whole lot with the bases because the bases pretty much are the same steps as the acids. It's not a whole lot different. There's just one little added tidbit at the end, especially if you're trying to calculate pH, right? You would do the POH and then you need to subtract it from 14 in order to get the pH. But reviewing of the definitions, Arrhenius produces the hydroxide ions in solution. Bronsted-Lowry, we're talking about proton acceptors here. And in basic solution, the pH should be greater than 7. And when we're talking about our metal hydroxides, the hydroxides that are strong are going to be your group 1, your calcium, strontium, barium are considered strong, although we did do the KSP of calcium hydroxide, and you would notice that it's in that slightly soluble category, so it doesn't completely dissociate. Keep that in mind too of talking about our hydroxide. But what we're going to be focusing on most of the time for the base equilibrium now is going to be looking at the weak bases, not the strong ones. And the weak bases are going to be looking like mostly, of course, ammonia is one of them. And then you're going to see other ones with like amine groups on there. these amine groups, because they can accept an H. Anything with like an amine group on it is definitely going to act as a weak base. There's not a whole lot of the weak base kind of compounds out there. In the back of your textbook, I think on 1063, they have a little short list of the weak bases with the KBs on there. There's not a whole lot of them. Ammonia is definitely the most famous out of the weak bases, so keep that in mind. Reviewing how to write the expression, it kind of goes the same way for the bases. You would put the products right here, concentration over the reactant, not including the water. Concentration doesn't really change. Equilibrium expression, same idea here. It's going to be that same pattern, the two ions on the top, the original base or acid on the bottom. And this time it's Kb instead of Ka because we're talking about bases. Okay, so once again, you're welcome to use any of these equations at the end when you're trying to calculate pH. You can go from the Kw equation and then do negative log of hydrogen. Or you can do the POH first and subtract it from 14, but do realize you have that little extra step at the end if you're calculating pH. Calculate the pH of a 2 molar solution of ammonia. So let's go ahead and start this out. What's the first step again? Reaction. And what's our reaction going to be here with the Kb? Reacting with water. Good. We're reacting with water. Now, which way is this going to work? Who's the donator here? Water. This is now acting as the acid. So the H is going to come off of, and we're going to attach it to the ammonia. And when we do that, we end up making ammonia. And then, of course, what's left of our water here is just a hydroxide. So we have our hydroxide, and this is why it's making a base here. It's producing that hydroxide, as you see. Now we're going to continue on. Our initial concentration is 2. The water, okay, over here, 0, 0. So, once again, if you see everything's 1 to 1, subtract x, add x, 2 minus x, and x. Write out the expression if needed. So, Kb is the ammonium on the top concentration times the hydroxide concentration over the original amount of the ammonia. Now we can substitute in, and we get Kb equals x squared over the 2 minus x, and our Kb is a 10 to the minus 5. So what do I definitely get to do? Eliminate the x, make it easier on yourself. X too small to really matter on the bottom there. 1.8 times 10 to the minus 5 here. What do we get for our x value? 0.0060. Good. All right, and that's going to represent the ammonium and the hydroxide because it's 1 to 1, so they're making the same amounts there. And since we want the pH, this is actually our concentration of hydroxide, so what can we do to that? Negative log it, and that's going to give us the POH. What is the POH? 2.22. Then what do? We've got to do 14 minus the 2.22, and that's going to give us our pH, which is 11.78.
So at the end, we just use
No, remember the significant digits for the pH value are the ones after the decimal. So that 11 doesn't count as part of the significant figures. So remember, yes, over here you would count 2 significant figures, which would be 2 decimal places to the right. Yes, good question, good review. But what you should notice about this entire problem, it's pretty much the same pattern that we just did with the acid one. It's x squared over the original minus the x, but you get to eliminate the x, equals the Ka or the Kb. So they become pretty standard. They're formulaic. Pretty much showing you the same setup. So when you get to the point, hopefully you'll get to the point where maybe you don't have to write out the Rice chart each time. Because it's going to be x squared over the original minus x. Basically, you're just seeing that pattern coming about. If you're not there yet, though, you continue, write out the Rice chart, do all the steps, and hopefully, yes, you'll eventually get to that point where you'll be able to do that and eliminate that extra step. But as you see, it's the same pattern. Pretty much the exact same thing that we did with the acids. The only thing that's extra is this little part where you have to subtract it from 14. Now for polyprotic acids. Polyprotic acids are the ones that can have more than one H that they can give to the solution. So this is going to be like phosphoric, like sulfuric, phosphoric. These guys have more than one H on them, so they have the ability to donate more than one H. But there's a couple things you need to realize about polyprotic acids. They dissociate in a stepwise manner, so the H's don't all come off at once. The first H has to come off, okay, and then you get its conjugate. The conjugate ends up being the acid for the second reaction. So then another H will come off. And if it's like phosphoric or phosphorus, then you would have a third step where that conjugate now becomes the acid for the last step. The problem, though, or the issue with these is only the first H really counts when it comes to determining the pH. The other two are so small in their amounts that they ionize that they don't really affect the overall pH. So the first dissociation is actually the real one that we care about. For sulfuric's a little bit different because remember that first H that comes off of sulfuric is strong. So that one completely dissociates off. The second one, though, does have a Ka and it is weak for sulfuric. So you would then have to apply the Ka, the Rice chart kind of problem solving to do the second H off of the sulfuric there. Any questions about the polyprotic before we move on to actually doing the stepwise problem? I'll show you the math that goes along with it. I mean, if you really wanted to break down each step. However, you'll see at the very end, after breaking down each step, that really the only first dissociation actually drives the pH value. Looking here, we're going to first write out the reactions for each. Then we'll begin the problem. So we're going to do the reactions, the dissociations, where we pull off each proton for each particular step, because it is a stepwise manner, as we just said. So the first one starts out with our phosphoric acid, and we're reacting it with what again? React with the water. Okay. Now, in this case, the H donates over, correct? So we still get our hydronium. And we get dihydrogen phosphate, where we now have a -1. Every time you pull off the H, you add 1 to the charge of the conjugate left there. Now its Ka is 7.5 times 10 to the -3. To do the second reaction in the step, like it said on the previous slide, this is the conjugate base. It now becomes the acid in the second step. So it's going to start the second step. And we still get hydronium. But our conjugate base now, we take an H off of this guy. It's going to transfer over to the water. So now we have just hydrogen phosphate. It has a -2 charge to it because we've now taken 2 H's off. Just keep adding a -1 to that. Its Ka, though, as you should see, is also, and it's very small, that's 10 to the -8, telling us that it's not going to do a whole lot of ionization there. Then this guy right here, the hydrogen phosphate, becomes the acid in the last dissociation step. So that is going to be HPO4 -2 plus the water. Still getting hydronium a little bit, very tiny bit at this point because you see that's the 10 to the -3 value, 13. 10 to the -13 is very small. And then we just end up with phosphate as the conjugate base. And this would be 4.8 times 10 to the -13. So that is how you would break down the dissociation reactions and break them down and dissociate them. So if they asked you to do that in a free response question, like write out the steps for the first and second dissociation of carbonic acid, this is how you would do that. Let's go ahead and set up the first one, because the first dissociation is the important one in terms of the pH. Let's go ahead and set that one up. In this case, as you can see, still everything is just 1 to 1 because it's only 1 H being moved. Do we need to set up the rice chart? You want to go right to it, or you want to set up the rice chart?
Right there, right there.
All right, so because we basically know that this is going to end up being what? This one's going to be X, this one's going to be X, and what's this one going to be? 1 minus X, right? Everybody understand that? If we set up the rice chart, that's exactly how it would end up being. So our Ka expression, 7.5 times 10 to the -3 equals X squared over 1 minus X. Now, what do we need to consider? Need to consider the elimination, right? Can we eliminate? No. Based on what I told you, you can't really eliminate. I can show you why mathematically as well. Here you would need to graph it. If I eliminate it, let me show you. We eliminate it, X ends up being 866, right? If you were to then divide that by the 1 times 100, how much percent gets ionized? 8.7%. So is that a value above 5? Yes, this is above 5. So this one, we can't do that. We have to keep the X value in because that ionizes above 5%. So we must keep our X value in, and we have to graph it. So in this case, we're going to graph it. So let's go ahead and do that. Stick it in there. Get your intersection, and make sure that you don't waste your time trying to find the intersection. Let it just do, hit, enter through the first curve, enter through the second curve, enter through the guess, and let it pop up the intersection for you. Don't waste your time trying to find it, because I think people do that and then they end up with the wrong value. All right, so by graphing it, remember this is y1, this would be y2, and of course this is not correct, so we can't eliminate here. And I knew that because I looked at the Ka and it was 10 to the -3. I knew that it was probably not going to work out very well, so definitely graph it. When we put it in and graph it, what do we end up with our X value to be? 0.083, correct. Did you get 0.083? That would be the right. You didn't get 0.083. So we'll definitely need to go back over our graphing. Yes? No? Is it 0.083? You got that? Everybody got that? If you're not getting that, in just a minute I can go back over the graphing with you. All right, so this is our molarity of our hydronium. This is also the molarity of our dihydrogen phosphate. It's only a -1. I keep wanting to make it a -2. It's a -1. So that is the molarity of both of those. So technically, we would stop here, and we would just negative log this and get the pH, because we know the second and third steps shouldn't affect the pH, because we just know that, because I told you that. But in a moment, I'm going to do the second step, and you can see how it doesn't affect the pH. So, we negative log. What do we get for our pH value? 1.08. Good. That would be the correct pH for this particular problem. Now, to do the second step, though, we wanted to add that in, even though, like I said before, we know that it's not going to work. What we would do here is we would start with our concentration of our dihydrogen phosphate. The concentration, this now becomes the original on the bottom. So that would go on the bottom of the expression. We would also be using the Ka for the second reaction. That would be what we would be using, the Ka for the second reaction. So let's go ahead and do that. It is 6.2 times 10 to the minus 8. What's going to be on top again? X squared. We know that's going to be the same. And what would be on the bottom this time? 0.083 minus x. In this case, could we eliminate x? Definitely, because that's a minus 8. That's really small. So what do we get for our x value here? Once you solve this, what would you get for your x value here? 7.17 times 10 to the minus 5. What you got? All right, so if we wanted to add the two ionizations together, 0.083 from the first one. This is from your first step. Adding this one in is going to be, 0.00071, right? Adding that up. So the 7.1 is going to just drop off anyways because it's not part of the sig figs, right? The pH still ends up being 1.08 because the sig figs that past that will not count. So does everybody see why doing the second step is kind of a waste of time? Because it doesn't really affect the overall concentration anyways. And we're good. Now for the salts. Salts are always fun. Salts are complicated. Salts you have to really think and pay attention to which salt you're looking at, and you really have to know your strong acids and bases. Strong acids and bases here to apply to the salts. Salts can behave as acids and bases when they're put in water. They break up into their ions, and some of the ions that they break up into can, react with water. And when they react with water, they create either an acid or a base. So salts are important. They can behave like acids and bases. Some of them are very neutral as well. And we'll talk about the characteristics that go with all of these. So salts are important. How can salts act like acids and bases? When they dissolve in water, they actually react with water. So here, a strong acid, strong base. So we have HCl, okay, or in this case, the sodium belongs to the hydroxide. So as you can see, our K would be on a OH, Cl would be on hydrochloric, HNO3. So the nitrate is the conjugate of the nitric acid. The chloride is the conjugate of the hydrochloric. The K is the cation of the hydroxide, the strong hydroxide. Sodium also would be the cation of the strong hydroxide. So when you see a combination of the cation and anion of both strong and strong, it's going to give you a neutral solution. So it's not going to change the pH. So like NaCl, because Na is the cation of a strong base, Cl is the anion of the strong acid, it doesn't really change the pH at all. Okay? They both will not react with the water, and the water basically it'll stay at 7, stay as a neutral solution. Let's look at the ones though that do actually react. So strong is always going to stay at 7, but you're looking at the cation. So if it's an alkali metal, or calcium, strontium, barium basically, those ones are the cations of the strong bases. If you're looking at the nitric, perchloric, so you have perchlorate, chlorate, the bromide, iodide, chloride. These are all the anions of the strong acids. Okay? Those are the ones you're looking for, those combos in the salts to figure out if it's going to actually react with water. Forming a basic solution is formed by the anion of the conjugate base of a weak acid. So if you're looking here, remember sodium would be like NaOH. That's from a strong base, so that one doesn't matter. But if I put F on with H, that's hydrofluoric, right? So F minus is the conjugate base of a weak acid, right? So if I put NaF, in solution, it's going to break up into the sodiums and the fluorides. But what happens now, this guy is going to do what? It's actually going to react with water. It's going to pull off an H. It's going to create HF. But also in that process, it ends up making hydroxide. So because it is a conjugate base of a weak acid, it's going to still react with water. It's going to pull off H's and create hydroxide. When you create hydroxide, what happens to your pH? pH increases and you become basic. Yes, this is a basic solution now. So looking here, K once again belongs with hydroxide, so that's strong. This is strong, we don't have to worry about it. But what's that? That's acetate. So acetate would be acetic acid. Is acetic acid a weak acid? Yes. So is acetate going to react with water? Yes, acetate would react with water, and it would pull off an H. Pull off an H, create acetic acid, but it also creates hydroxide. Once again, we increase hydroxide levels, you increase your pH, and you are a basic solution. So that's how the conjugate bases of the weak acids will, if they're in a salt, they will create basic solutions. Now, acidic solutions are created from the conjugate acids of the weak bases. This is pretty much one of the examples we're going to use here, because ammonium, what is ammonium related to? NH3, ammonia, this is the conjugate. This is the conjugate acid of ammonia. Chloride, we know, goes with hydrochloric, right? This one's HCl. This is strong. We don't have to worry about it. It's not going to affect the pH. But if I have hydronium in water, it's going to react with the water. What's it going to do? It's going to donate an H. It's going to create ammonia and hydronium. It's going to make some hydronium in that water. If you make hydronium, what happens to your pH? Decreases. If you're decreasing your pH, you're now becoming acidic. So yes, regular salts putting in water are not always just regular neutral 7. Some of the salts that you are using in the hand warmer lab, would some of their pHs would have been above or below 7 based off of this concept here. So, when you're looking at the salts, pay attention to their conjugates. If it belongs to a weak, then you have to look at it and say, okay, it's going to react with water and drive up or drive down the pH. Now, if you have conjugates of both, what do you do in that situation? You have a conjugate of a weak acid and a conjugate of a weak base as part of the salt. Any ideas there? Well, you really have to pay attention to the Ka and Kb values for those. If you have a conjugate of a weak acid and a conjugate of a weak base, both in the salt, it's going to be like which one's stronger out of the two, so you have to look at their Ka and Kb values to figure out which way the pH will go. If the Ka, was stronger, the conjugate of the acid there, it would ionize more with the water and decrease the pH. If the base part was stronger, it's going to pull off the H and create the hydroxide. So you really have to pay attention to those Ka and Kb values. So here's an example of one, the aluminum. The aluminum hydroxide would be a weak base. The sulfate is a conjugate of hydrogen sulfate, and therefore would be a weak conjugate as well. So you'd have to pay attention to both their Ka and Kb values to figure out which one is the stronger out of the two, which one would ionize more, and then from there you would know the pH level, whether it would go up or down. These ones are more of the important ones that you have to memorize. So when it's a neutral with a weak conjugate, if it's the base of an acid, the conjugate of a base of a weak acid, that's going to be basic solution. If it's the conjugate acid of a weak base, it's going to be acidic, with a neutral on the other side of things. You really, really have to memorize those strong acids. You really, really have to memorize those strong bases so you can tell the weak ones and pick them out of the salts. So here it also compares and tells you that the Ka is stronger, or this is a higher number than the Kb, then you know it's going to be acidic. The Kb versus the Kb is then it's going to be basic. Kb is larger. Equal, then it would be 7 neutral. These are on your notes already for you, but this is in case you have a weak combination going on. Now, this is a particular take on some of those problems here, because we want to calculate the pH of 0.75 molar of sodium cyanide. This is the salt we're going to dump into the water, the sodium cyanide. Then it also tells us the Ka for hydrocyanic acid. So I have to look and decipher my salts before I begin. So I'm looking here. Does the sodium matter? Is sodium neutral, or is it going to create something in solution? Sodium's a cation of a strong base, so no, this one's not going to matter. The cyanide, though, goes with what? The hydrocyanic acid. Is hydrocyanic acid a strong acid? No, it's not one of the 7 strong. So this one's definitely a weak acid. So we need to pay attention to the cyanide. The cyanide is going to react with water. So cyanide reacts with our water, and what happens? Cyanide pulls the H off the water and creates HCN, but also in that process we get hydroxide, so it's going to be a basic solution. So this here is our reaction. And since we haven't done one in a while, I'll just write it out here. So we have 0.75 molar of this, 0 and 0. We're going to lose X out of that. We're going to gain X over here. So 0.75 minus X, X, and X. So far, so good. Setting up the right chart. However, cyanide is acting as a base here. What do we need? What value do we need in order to finish this problem? We need a Kb for this, right? Does anybody remember something that we can do if we know the Ka of the acid? What can we do to find the Kb of the conjugate base? Kw definitely equals Ka times Kb. So yes, we could take our Kw and divide it by the Ka. So 1 times 10 to the minus 14 divided by our 6.2 times 10 to the minus 10. That should give us our Kb value that we can now use and finish off the problem. So what is Kb going to be? Kb is 1.6 times 10 to the minus 5. Anybody get that? All right, so now we know our Kb, so I'm just going to set this equal to x squared over 0.75 minus x. Because we're following the expression here, products over reactant. Do I get to eliminate x? Minus 5, definitely get to eliminate x. So we're going to calculate, get our x value. What'd you get for your x value? 0.0035, right? Now, remember, this, though, is the concentration of H3N or hydroxide. We want to focus on this one, because what can I do with that hydroxide to start figuring out my pH? I negative log that, and I get my pOH, right? So, negative log, that's going to give me my pOH. Now, this is pOH that we're getting. So, what is that value? 2.46. Remember, 266, since this has 266, that's 2 decimal places to the right. Now what can I do to figure out the pH? 14 minus, and I get 11.7, no, 54. 11.54. Thank you. This is now my pH. So, for the salt ones, pay attention to which Ka or Kb value they give you. You might have to do the Kw equation with it. Still is kind of the same idea of the Rice chart, figuring out the amount ionized, and then being able to go and figure out the pH from that. I worked it all out, but it's in the PowerPoint here, so you're welcome to check it out. About Lewis and acids and bases. The Lewis acid is the electron pair acceptor, and the Lewis base is the electron pair donor. So it's kind of the opposite idea of the Bronsted-Lowry definition, where we're talking about the donors and acceptors. Except for what you're donating and what you're accepting are different things. A Lewis acid is going to accept a pair of electrons. The ones that is attracted to the electrons, we call them the electrophiles. And the ones giving away the electron pair donor that wants to go to that space, those are the neutral philes. Those are terms used in organic chemistry that you'll be familiar with if you take organic. Especially if you're doing anything in the medical field, you'll be taking organic. But what you're seeing here is basically the aluminum plus 3 has lots of empty space in its shell there. It's 3, has a lot of room in that 3 shell, so it can accept electrons. So the water donates a pair each time, and it's creating one of these complex ions that you saw when you read chapter 17. The complex ions are pretty cool because usually they make lots of pretty color solutions, and they will do lots of reactions for us that are interesting. But what we're seeing here is that in order for this complex ion over here to form with the aluminum and the waters, you have the aluminum being the acceptor and the 6 waters all donating a pair each time. A more simple example for you would be like adding H plus onto ammonia. Okay, so the H plus has like empty space, and the ammonia has the pair. So when you allow the H to attach onto that pair, what do we create? We get ammonia. So this is a more simplistic example of the process. A good example of a Lewis acid-base donation here would be how ammonia grabs onto an H, creating ammonia. So that's definitely a more simplistic version. But all of the complex ions, the ones that you read about in Chapter 17, are created through the Lewis acid-base definition. Like I said, you don't have to know how to write out the reactions for those particular complex ions, but sometimes they throw in those reactions for something for you to work with in the free response. So you still should be able to do like the stoichiometry with them. You should still be able to, and the ferrous ammonium sulfate that we used in the hydrogen peroxide lab and the permanganate redox titration, that was a complex ion as well. So you'll see them being used, so you should be able to use them from a stoichiometry molar ratio aspect. And you saw this chart too, because when you were working with it, you were using the Kf values for them to create the complex ions. As you can see over here, these are the complex ions that are being created. And a lot of times you have ammonia as a ligand, you have cyanide as a ligand, hydroxide can be a ligand. These are the ones that are attaching to that central atom. Remember we drew Lewis dot structures last year? The ones attaching to the central atom were called ligands. And here's another example where the copper is allowing for 4 ammonias to attach, 4 base, the pairs here going to attach to that copper in the center. And one thing about knowing about complex ions is that the charge on the central atom, if you double that number, that's usually how many ligands can attach. So since this is a positive 2, double that number to 4, so you see 1, 2, 3, 4 ligands are going to attach to that central atom. And it forms the complex ion over here. Still has a +2 charge because the 4 ammonias being added don't have a charge on them. But, like I said, you don't have to actually write them out or draw them out like in this particular aspect, but if they give you the formula for, this copper with the ammonia complex ion, and they give you the mole ratios and things, you still should be able to do the stoichiometry with it. One last little slide here looking at the other thing about the solubility, because this was in the KSP section, is that when you do add, ammonia to something like silver chloride that is pretty insoluble, it actually breaks it up and attaches to the silver and creates the complex ion, and in doing so, it makes it a lot more soluble. So it does affect creating these complex ions, and you saw those Kf values. It does affect the solubility. It does increase the solubility of more insoluble salts. Last but not least, this is already on your notes, but it kind of puts all 3 together at once, so you can compare them. Definitely need to know all 3 definitions at any time to be able to explain them conceptually. Any questions?